In 6.2, we're going to talk about exponential functions, and this is just going to be a basic overview of exponential functions and their graphs, solving some exponential equations, and then looking at some application problems. First of all, when we say exponential function, you might have heard the term exponential growth, and that is modeled by these exponential functions. So an exponential function is just a function that has some base a that's raised to the power of x. So this time the variable is the exponent. And this base a is just going to be some number. It's going to be greater than 0, so it's not going to be negative. And it's also not going to be 1. And the reason why we have those conditions there is so that we have a function, but not only a function, but a one-to-one function. Now recall that if a function is one-to-one, it does have an inverse. So later on, we're going to talk about the inverse of an exponential function. So anyway, that's why the base has to be greater than 0 or positive and not equal to 1. Let's go ahead and sketch two different exponential functions. And again, they're called exponential functions because the variable is in the exponent. F is going to be equal to 2 to the x, and g of x is going to be equal to 1/2 to the x. So notice that these are very similar. F of x is base 2, g of x has base 1/2. So we just took f, the base of f, and we flipped it, and that became the base of g. And I want to do that so you can look at the difference between the graphs if you decide to flip the base. I am going to use, let's do green for f. And I'm going to go ahead and rewrite that as y equal to 2 to the x. Make myself a table of values. I'm going to start with 2, then go 1, 0, -1, -2. And just plot some points, see what they look like. So if x is equal to 2, and here I'm looking at f of x equal to 2 to the x. If x is 2, that's 2 squared, which is 4. If x is 1, 2 to the 1 is 2. If x is 0, 2 to the 0 is 1. If x is -1, remember 2 to the -1, I'll do this below, says we're going to flip and make the exponent positive. So 2 to the -1 is just 1/2. And then 2 to the -2, flip, it becomes 1/2 squared, which is 1/4. Let's go ahead and graph these points. I'm going to pass through 2, 4, 1, 2, 0, 1, -1/2, and -2, 1/4. If I kept going, I would, let me just go ahead and connect these with a nice smooth curve. If I kept going and looking at larger x values like 3, 4, and 5, and so on, this will just keep growing. Now I'm going to label this F. If I look at smaller x values like -3, -4, this graph is going to get smaller and smaller and smaller, but it's not going to cross over the x-axis. So the y values will never be 0 or negative, which makes sense. Look at our y values. They're always positive. Whether x is 0 or positive or negative, the y value will always be positive. So it turns out that this will be a horizontal asymptote here at the x-axis for our function f. And that would be y equal to 0 would be a horizontal asymptote. I'm going to use blue for g of x, replace g with y, and graph 1/2 x by making a table of values. Now remember what we did. We took the base 2 of f and we flipped it, and it became the base 1/2 of g. So if we flip the base, we're actually going to be flipping the graph. and you'll see which axis we're going to flip it on. I'm going to do the same x values, 2, 1, 0, -1, -2. So 1/2 squared is 1/2 times 1/2, so that would be 1/4. 1/2 to the 1 power is 1/2. And you can see I'm getting the same values, but they're flipped, right? 0, 1/2 to the 0 power is 1. 1/2 to the -1. Remember, we flip, so it's 2 over 1, and it becomes a positive 1 exponent, which is simply 2. And if we did 1/2 to the -2, again, you could put this in a calculator. You would flip. It's 2 over 1 squared, which is 4. Graphing these points, 2 goes through 1/4, 1 goes through 1/2, 0, 1. -1 is 2, -2 is 4. And then you can see, if I continue on with this graph, that it's just a reflection across the y-axis. So I flip the base, I also flip the graph. Now if you notice our graph F, it starts out small and it grows. And that's because the base 2 is bigger than 1. Whereas G starts out high and then it gets low and approaches that same horizontal asymptote. So they have the same horizontal asymptote. And that's because the base of G is less than 1. So if the base is greater than 1, it always goes low to high. If the base is less than 1, it goes high to low. And the graphs will always have that same basic shape. Something else we should note is it didn't matter which base we chose. They both had the same y-intercept of 0, 1. They both had the same horizontal asymptote. And in fact, if you look at domain and range, that would be the same as well. So we can put in any x value, but look at the y values. They're never 0, they're never negative. The y values are always greater than 0. And that brings us to these properties that we have below. Properties of exponential functions of this form, some base a to the power x. Domain, all real numbers. Range, 0 to infinity, but don't include 0. Horizontal asymptote, y equals to 0. The y-intercept is the point 0, 1. There is no x-intercept, and there's no vertical asymptote with these exponential functions. But that's if it's not translated or transformed in some way. So what happens if we do transformations? Are they going to be the same as our prior transformations? And the answer is yes, they will be the same. If you change the x, it's going to do the opposite of what we think it's going to do. If you change the y, it's going to do exactly what we think it's going to do. So an example 2, and we'll just do one of these transformations. That's not really the focus here. It's more to get a basic idea of what an exponential function looks like and know that it behaves the same as far as transformations go as our prior functions. In example 2, this is 2x to x minus 2 is the exponent, and then we have a minus 3. If we look at our base or parent function, it would be y equal to 2 to the x. And I am going to graph that. It's going to pass through 0, 1, 1, 2, 2, 4. It's going to go up half, and then it approaches. So that would be y equal to 2x. The next the first transformation, would be the x minus 2. So I'm subtracting 2 from the x. It's going to do as we saw before. When you minus 2, you're actually going 2 units to the right. So we're going to take all of these key points and we're going to move them to, maybe I'll just pick the really nice ones. Well, half is okay. We're going to move them all over 2. 1, 2. And we're still following along that horizontal asymptote. That hasn't changed. So this would be y equal to 2 to the x, y equal to 2 to the x minus 2. And then that would just be a shift right by 2 units. So it did exactly what we thought it should do. And now if I look at that minus 3, function's already done its job. The exponential function did its job. So that minus 3 is going to affect the y value. It's going to shift down 3 units. And I'll just write shift down 3. So let's go ahead and move 1, 2, 3, 1, 2, move all of these, 1, 2, 3, these 3 key points down 3. However, think about the shift down. That means we're also moving our horizontal asymptote. So we're going to shift our horizontal asymptote, HA, down as well, 3. Let me go ahead and sketch in that horizontal asymptote at -3. And then we will finish off our points and sketch our graph. Maybe I'll put this in a different color. Maybe I'll make it black so it's clear that this is our final graph, F. And I can also check these points to make sure it passed through the correct points. Let's look at these 3 key points when x is 4, 3, and 2. So if x is equal to 2, y is equal to 2 to the 0 minus 3. 2 to the 0 is 1, 1 minus 3 is -2. So is my graph passing through the point 2, -2? Yes. We'll go ahead and check x is equal to 3 and x is equal to 4 as well. This would be y equal to 2 minus 3, and that's -1. So are we passing through 3, -1? Yes. And then the last one would be 4 minus 3, or +1. So is it passing through 4, 1? Yes. Okay, so the next thing we want to look at, and this is really important when we talk about things growing exponentially, is this special natural exponential function. The base here is what we call base E. And base E is similar to pi in that its number form has a decimal part that goes on forever. It never ends and it never repeats, well, as far as we know. Same with pi. The reason why we use that symbol to represent an approximate value of 3.14 is because pi goes on forever and ever and ever, and we can't write the number forever and ever and ever, so we chose a symbol to represent approximately 3.14. The value for E is approximately 2.72. This is a little bit smaller than pi. So where pi is used to describe either the circumference or the area of circular objects, what base E is used for, and the reason why we call it the natural exponential, is because when you have continuous growth, as we do in nature, say if you're looking at bacteria and how it grows continuously and it grows exponentially. It'll grow at a rate of base E. So things that grow naturally in nature continuously, could be a rabbit population, they typically grow at base E. So it occurs a lot in nature. We're going to go ahead and sketch the graph, but remember E is approximately 3. So when I sketch the graph, the base E is greater than 1. I know it's going to go low to high. I know its basic shape. I know its y-intercept. I know its range, its domains, and I know its horizontal asymptote. I just have to find some points. And here you're going to use a calculator for this, definitely. If you don't have the E button on your calculator, you can just use the 2.72. Let's go ahead and make a table of values. I am going to substitute y for f of x. And I always use the same values when I graph exponential functions. I always do 2, 1, 0, -1, -2. That gives me enough points to get an idea of what the graph is going to look, the points that the graph will pass through. So if I look at e squared and I plug that in a calculator, so e is less than 3, so it's going to be less than 9, and I get approximately 7.4. So at 2, I'm going to go, oh, now my graph is a little bit too short, but that's fine. If we put in e, we know that's approximately 2.7. Would be close to 3. If I put in 0, e to the 0 is 1. -1, that would be e to the -1. Now in a calculator, you would get about 0.4. But remember, that's the same as 1 over e, about 1/3. So that makes sense. And then e to the -2 in a calculator is about 0.1. So that's about 1 over 9. Draw my graph. It does exactly what I think it's going to do. It's still passing through 0, 1. That's still a y-intercept. I still have the same horizontal asymptote, which is y equal to 0. However, like on our previous graph where the base was 2, this base is larger than 2. So it actually grows faster. It gets steeper faster. And you'll find that the larger the base, the faster it grows, which makes sense. What we're going to do next is touch on how we solve exponential equations. And again, we're going to look at all this stuff later on in other sections. But basically, we're going to use this property that if you can get the bases to match, so you have base A, the only way that this equation can be equal is if the exponents are equal. So that's the basic idea when you're solving these exponential equations, is first see if you can get the bases to match on either side of the equal sign. So for example, in part A, I have 3 to the 2x minus 1 is equal to 27. And I see I have this base 3 on the left-hand side, and I know I can write 27 as 3 to the third power. So this becomes 3 to the 2x minus 1 equal to 3 to the third power. And by that property, the only way this equation can be true is ignore the base, you can cancel them, is if the exponents are equal. So that would be if 2x minus 1 is equal to 3. And now I have to simply solve for x by adding 1 to both sides and dividing by 2. And I get that x is equal to 2. I could check that. I could put that back in for x and I'll get 27 is equal to 27. So again, we can also write this in set notation as a set containing 2. Well, let's do a few more examples. In part B, I can see that I have a 5 on the right and I have a 1/5 on the left. So maybe I will try to take that 1/5 and write it as 5 to some power. So I know that if I flip my fraction, that this will change to 5 to the -1. And then the x plus 3 exponent is still on the outside. So that helped me a little bit. But now I have that -1 inside the parentheses that I want to get rid of. However, this is simply multiplying exponents. So if I multiply the -1 times the x plus 3, this becomes -x minus 3. So it's 5 to the negative x minus 3 equal to 5 to the 2x minus 1. I got my bases to match. It must be true that the exponent negative x minus 3 is equal to the exponent 2x minus 1. I think I'm going to add x to get 3x on the right, and then add 1 to get a negative 2. Oh, look at that. I was supposed to have a plus. Thought something looked weird. Typical me. Okay, so I'm at a minus 1, and this becomes a minus 4. So dividing by 3, I get negative 4/3 is equal to x. Okay, let's do a couple more. If we look at C, I see the 7 underneath the square root on the left-hand side, and on the right I see 49, which I know is 7 squared. But the 7 is underneath the square root on the left. So what I want to do first is get rid of the square root by writing this as 7 to the 1/2 power. And then that's raised to the x. The 49, I'll write that as 7 squared. So I'm trying to get them to both have base 7 on either side of the equal sign. On the left, to get rid of the parentheses, I would multiply 1/2 times x, and that's simply 7 to the x over 2. And then on the right, I'm going to flip and make this a 7 to the negative 2 power, so that I have the same base 7. This becomes x over 2 equal to negative 2. Multiplying 2 on both sides, x is equal to negative 4. So you see the idea is just to get the bases to match. So first of all, you have to identify what your base is going to be, and then you have to get them to match. Last one. Let's say I have 3/5 in the parentheses and I have 9 over 25. Now I know 9 is 3 squared and 25 is 5 squared. So I'm thinking that the base that I'm supposed to match to is 3/5. I'm not going to do anything on the left-hand side. On the right-hand side, I'm going to write 9 as 3 squared and 25 as 5 squared. So notice that properties of exponents, now I'm working on the right, that's 3 over 5. I can take the square out since it's the same exponent in the numerator and in the denominator. So this whole 3/5 squared is to the x plus 4 power. And on the left, it's still going to stay the same for now. On the right, if I multiply the exponent 2 times x plus 4, then I could get rid of that bracket, and this becomes 3 over 5. 2 times x plus 4 would give me 2x plus 8. Now I can cancel because I have same base. And we have negative 2x is equal to 2x plus 8. I'm going to minus 2x from both sides to get negative 4x equal to 8, and then divide by a negative 4. I get x is equal to negative 2. And we can check all of these solutions either by hand or by calculator. They should all work out. The last thing we're going to touch on in this section is an application that you may be familiar with, and that's computing the amount in an account. So the interest that you earn, that formula is actually an exponential equation. We'll start out with what we call compound interest. So compounded interest just means that we're going to compute the interest a certain amount of times during the year. This A of t, this would be the amount that you have in your account after a certain amount of time. P is what we call the principal, and that's the amount you start with. That's the amount of money you're going to invest. And then the formula is 1 plus R. R is your interest rate. N is the amount of times that you compute interest, or the amount of times you compound the interest per year. And we're going to raise that to the exponent n times t. T is the years that you are investing the money in an account. And it's kind of a hideous formula. But first of all, we want to talk about some language here when we talk about how many times we compound interest. So if you see the word annually, that just means that you're going to figure out the interest once per year. So the n would be 1. So n is how many times you compute the interest, or we say compounded per year. Semi is half, annually is a year, so half a year means you're going to compound the interest twice. So n is 2. Quarterly means you're going to compound or compute interest 4 times a year, so n is 4. Monthly, 12 months in a year, so n is 12. Daily, unless it's a leap year, it should be 365. Let's use that formula, and you're definitely going to need to use a calculator here. In example 5, let's say that we are going to invest $3,000. Our interest rate is 2.4%, and we're going to invest over a 5-year period. We want to find the amount in the account for the interest if it's compounded annually or monthly. So let's figure out what all our variables are. It says find the amount. So since we're finding the amount, we're trying to find A. We know that we start out with $3,000, so that's going to be our principal P that we invest. The interest rate is 2.4%. That's R. We're going to have to translate that to a decimal, not a percent. And since we're investing over 5 years, 5 is going to be our T value. So if we're going to compound the interest annually, as in part A, that means my N value is going to be 1. So now my rate R, if I were to write it as a decimal, remember we're going to move 2 to the left, becomes 0.024. Let's put all of this together. The amount in the account after 5 years, so A of 5, is going to be equal to the principal, which was 3,000, times 1 plus the interest rate would be 0.024 over n. N is 1, and it's going to be raised to the n, which is 1, times t, which is 5 power. I'm going to clean this up a little bit before I put it in my calculator. 1 plus 0.024 is simply 1.024. And then 1 times 5 gives me the 5. When I put it in my calculator, I'm going to round to 2 decimal places because that's traditionally how we round money. But if you're working on a problem and you're instructed just to round it to the nearest dollar, you wouldn't do the 2 decimal places. But I'm going to go ahead and put this in. I get 3, and it's a dollar amount, 3,377.699, so 0.70. So that's the amount that I'll have in the account after 5 years if I put in $3,000 and the interest rate is 2.4. Now let's look at what happens if the interest rate is compounded monthly. That means that our n is equal to 12. So all the values are going to be the same, except for I'm going to have 12 for n. So A of 5, still 5 years, is going to be, we still start out with $3,000, and we have 1 plus 0.024 over 12 this time. And then its n is 12, t is 5. I am going to clean this up a little bit, which you don't have to, but I do know that 0.24, or 0.024, sorry, divided by 12 is 0.002. This becomes 1.002. And then 12 times 5 is 60. So I think I'll put that in my calculator. And I get 3,382.085, so 0.09. Something we should note is that we earned more money when the interest was compounded more often, and that's going to be the typical case. The larger the n, the more times you compound the interest, the larger the amount would be. So if you are investing money, you want to make sure your n is as large as possible. However, turn this around a little bit. This tells us how much money we have in an account if we're investing money. What if you're borrowing money? Then that A value, that amount, would be how much you still owe. So if you were borrowing money, you actually want your n to be smaller, so that amount that you owe is actually lower. Now, what happens if n gets larger and larger and larger, and that n value gets closer and closer to infinity? That leads us to our last formula that we're going to talk about here, and that would be our continuous compounding interest. So remember when I said base E is a continuous growth, it's a growth in nature, but it also models continuous interest. Notice that that ugly formula got really, really nice when our n went closer and closer to infinity, and we were actually figuring out or compounding our interest at every single second. So now we have that the amount in the account is simply equal to the principal, and then it's going to be base E to the rate times time. That would be our exponent. Notice that there's no n anymore because we're not figuring it out at certain intervals. It's a continuous interest. We're going to look at those same values. So our, oops, I don't want that. Our amount after 5 years, so all the values are the same, except for now, I'm going to take 3,000 times E in your calculator to the 0.024 times 5. I'm going to go ahead and write that as E to the, in my calculator, I got 0.12. Is that right? 0, 1, yes. So in the calculator, I get 3,382.49. So it went up a little bit from monthly. So again, if you're investing money, continuous interest is the way to go. So that wraps up this section, and that's it.